It's an absolute pleasure to be speaking here today, and I have to say it's the largest class I think I've taught to for a long time, so thank you for turning up. Let's see, could I first of all just acknowledge the Gadigal people of the great Eora Nation on whose ancestral lands we're meeting in this beautiful space today. And we recognise elders past, present and emerging who are the traditional custodians of knowledge, and knowledge is what we're all about. This is what we're here for. And when Donald reached out to me asking whether I'd like to give a talk about Antarctica, it was just trying to capture some of the elements of this extraordinary landscape. And at one level, one could just talk to props and try to get you to imagine what it's like. But I thought it was really important to actually show some images and movie footage just to try and give you a sense of this. We're about 30, 40 degrees warmer there than further south at the moment. But just ask, show of hands, has anyone been to Antarctica at all? Oh, fantastic. Okay, well, great. Well, hopefully have a chance to have a chat about this. And this is not a single effort, far from it. This is a huge amount of work with a lot of brilliant people, and particularly call out our great friend and colleague, Chris Fogwell, who's at the University of Plymouth. And I think it's really important as well, with everything happening internationally, to acknowledge the amazing Australian Research Council and the funding they do provide. And you'll see this logo of a flying penguin as well. This is Antarctic Logistics and Expeditions that support a lot of the work. Anyway, on to the show. Right, what are we talking about with Antarctica, and why is it such an important barometer? There's this lovely quote, I don't know if you've seen it at all. Below 40 degrees south, there is no law. Below 50 degrees south, there is no God. If anyone who's sailed south, you might know what that means. It's the wildest, most extreme environment you could imagine. And we're just going to actually give a bit of context here for where we are, coming straight south from Tasmania. This is a beautiful movie created by a team called IMBY. It's a vast area. It's basically twice the size of Australia. You get the classic elephant eel, which is known as East Antarctica. It's all relative to Greenwich. West Antarctica, which we're going to hear a lot about, which is relatively low-lying, and then the peninsula. Importantly, no permanent human population on there, and it's been protected since 1961 through the Antarctic Treaty, which is one of the most successful, if not arguably most successful international treaty. Virtually all the continent is covered with ice, and it's getting close to 1.6, 1.8 kilometers thick. And this is the paradox. It's almost entirely covered by ice, and yet it's effectively the world's largest desert. And if you go onto the plateau, you're talking somewhere in the order of about 20 millimeters of precipitation a year. So it's this extraordinary thing. It's a lot of ice. 70% of the Earth's fresh water is locked up in there, but it's actually incredibly dry. And in fact, hydrating yourself is actually one of the biggest challenges alongside keeping warm and managing your heat. But it's not that long ago, you know. Christine talked about this to Douglas Mawson, the great Sir David Edgeworth, out from Sydney. If you looked at an atlas from just over a century ago, most of it was unknown. It was just blank. The bottom third of the entire planet was unknown. Sometimes if you got a patriotic magazine or an atlas, you'd have the UK slapped on the top of it just to give you a sense of scale and ownership. But effectively, apart from a few orange bits, no one really knew what was down there. And it fueled this extraordinary expansion of exploration and discovery. And it was effectively the Edwardian equivalent of space travel. And it's captured all sorts of images. Many of you recognize the great Sir Ernest Shackleton, one of the great leaders and absolute inspiration for me, and these amazingly iconic images of these extraordinary people. This wonderful so-called advert for the Imperial Transantarctic expedition when they effectively got trapped in the ice, but you can't, advertising is just amazing. Men wanted for hazardous journeys, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful, honour and recognition in case of success. I mean, wow, marketing is fantastic. Sadly, it's probably apocryphal, but you should never ruin a good story with facts. Sorry, Christine. It's a great advert. But it's iconic, and people have this amazing imagination and connection, and it wasn't that long ago. We're talking a century. It's amazing. Now, one of the things that's often understated or forgotten about when you have the likes of Shackleton and Mawson and others and Scott, was they didn't just go south to suffer and come back with great photos. They went south to do research. And in fact, that's primarily what funded a lot of their work. So even Shackleton, with doing the trip, and even when he got trapped in the ice, we've collected that research data, the observations of the weather, and they're being used into the climate models today. So there's incredible value from these studies. And one of the reasons why in Australia we're particularly interested in it is it has a huge influence on our climate systems today. This is amazing footage. We should be really quite proud of this. This is from a so-called documentary called Home of the Blizzard, if those of you have seen it. This is from the National Film and Sound Archive. So it's Douglas and Mawson's expedition. So due south of Tasmania, several weeks of sailing and travel, in a place called Adélie Land, Commonwealth Bay. And this extraordinary footage is of the team from 1912. And this is called Home of the Blizzard for a reason. Some of the highest wind speeds in the world were recorded here, over 200 kilometers an hour, some of them. And this is the original hut, it's still there. And these extraordinary people, well, for just one of several bases, Mawson actually set up across Antarctica over about an 18-month, 2-year period. And if you don't know the story of survival, it's worthy of, it's just an incredible tale of survival. But we've all been absolutely amazing footage. So you can still see bits of this online, but it's the world's, officially it's the oldest documentary. I won't keep showing the footage, but extraordinary thing. And seeing that imagery for the first time went beyond paintings and pictures to suddenly making it a reality. The health and safety issues around this, and this I just don't want to know about. So we've got a number of ways you can visit and go down there. Many of you have been down, most of you probably went down by boat or ship, I'm guessing. And you've got the wildest, stormiest seas in the world. And they're incredibly important. In fact, the westerly winds are about 40% stronger than their equivalent in the Northern Hemisphere, primarily because there's no land basically blocking it. So it's uninterrupted flow. And that drives the ocean's circulation system. But the downside is when you're sailing across that, you tend to lose a little bit of weight. When you get down into the actual edge of the continent, you then meet this extraordinary area of sea ice. And this is from one of Shackleton's expeditions over a century ago. And this is one trip that we took just over several years ago. And it hasn't changed in that respect. You have this very recently formed sea ice where the surface of the ocean freezes, and then you're just pushing through and opening a way through. But it's just, it's an amazing experience to just go for that because it's so still and calm. And the next moment you could have a wild storm. Now, coming to the nuts of what we're talking about here with climate, it's an area that everyone's known is a potentially massive risk to us with regards to climate and environmental change. And you might be able to make out this picture up here on the top right. I'm not going to show lots of graphs, I promise, but this is extraordinary. This is from an incredible scientist called John Mercer back in 1978. So he was way ahead of his time, way ahead of his time. And from the very limited amount of work that had been done in Antarctica, he realized that most of the West Antarctic ice sheet was sitting on the seabed. It was sitting on the seabed, which is the hatch lines for those of you who can make it out. So unlike the East Antarctic, where a lot of it is sitting on rock above the sea, not all of it, but a lot of it, the West Antarctic is sitting on the seabed, and that's super important for our story and moving forward, because it's effectively being bathed in the ocean waters. And he pointed out, this is the title of the paper, West Antarctic Ice Sheet and Carbon Dioxide Greenhouse Effect, a Threat of Disaster, 1978. That was a long time ago he was raising out the point. Extraordinary scientist. And so Antarctica has a lot of challenges for us because the West Antarctic has got somewhere in the order of about 3.5 meters of global sea level rise. That's how much fresh water is locked up. So if you lost the West Antarctic and nothing else, sea levels on average would rise 3.5 meters. Now it varies around the world depending where you are, but that's the average. That's a lot of water, a lot of water. So for some of the challenges though for us working in Antarctica is that actually not many people have been down there for that long. We have a few token efforts of where people have gone down, like Shackleton, Mawson, a whole lot of great researchers a century ago, but those are snapshots, a year and a half, and then they sensibly get away. It was only since basically the Treaty of International Geophysical Year that actually started having continuous observations. So from the 50s, 60s. That's it, at those few bases for a continent size that's basically double the size of Australia. So we don't have many observations. We certainly don't go back that far. We don't really know how the ice sheets respond over long-term changes. We've got a good sense of the physics of it, but we haven't actually observed that. Which then begs the question, just how stable are these different ice sheets under a warming environment? So this is something that's often forgotten about as well, is when we step back and we look at climate and environmental change, the science of climate is really quite old. And in fact, it's probably arguably with Eunice Foote, the amazing Eunice Foote, who was a very early researcher in this space. She was basically the first one to point out the greenhouse effect, and actually greenhouse gases could drive change. In 1856, the American Association, and she wrote this very short paper, the highest effect of the sun's rays are found to be on carbonic acid gas, which is an old word for carbon dioxide. The receiver containing a gas became itself much heated. An atmosphere of that gas would give to our Earth a high temperature. The devastating thing is, actually, she wasn't even allowed to read her paper at that meeting, if you know the story, because she was female. It was actually a colleague friend who had to do it. She went on to become a suffragette in science, lost an amazing person. So there's a tragedy there in itself. 1856, though, that's a long time ago. Now, where are we? Well, for those of you who've been to Hawaii, Mauna Loa, the extraordinary NOAA Earth Observatory on top of a volcano, you can go there since the 50s. It's been monitoring carbon dioxide levels as one of the many greenhouse gases, but arguably the most important. We're now at the level of what we call 429 parts per million. That is well beyond anything natural. In fact, actually, we haven't seen anything like that since the Pliocene several million years ago. And then you had rainforests in Siberia and crocodiles in Kamchatka and all these other crazy things. So you're looking at a completely different climate system. The challenge for us with Antarctica is that was on the long-term impacts of the Pliocene. That was what the climate actually balanced out at. We haven't actually leveled off and reached equilibrium with what that 429 is, and it's still rising. In fact, last year was the largest single jump in carbon dioxide in 1 year ever on record. So even though we're actually getting carbon emissions, we're slowly getting them down, the actual levels in the atmosphere are increasing. And we're seeing the impacts. We're seeing the impacts in Australia. We're seeing the impacts globally. You can't open the newspaper or look online without some other record being broken. We're seeing devastating fires, awful flooding. South East Queensland, just one example, the cleanup, and of course the effects on our biodiversity. This is real and it's happening now. The question is, what do you do about it? Now, a lot of the scenarios and what we look at are typically based on this idea that we have a linear forcing, that actually over time, you increase carbon dioxide levels, the planet reaches an equilibrium, it gets hotter, sea levels rise. There's an important element to that, and conversely, if you can bring it down, great. But there's an elephant in the room. I don't know, has anyone read this book, The Tipping Point? Yeah, a few of you. It was a cracking read. He's just done a new one, The Return of a Super Tipping Point. Malcolm Gladwell, he really introduced this concept into the public vernacular. And you can show all sorts of nerdy graphs about what tipping points are, and I could try to illustrate it with a chair, and I won't ask you to do this, but one example is basically when you sit on the chair and you lean back, there's a certain point at which, if you let go, you'll fall forwards. If you have lots and lots of wine and you keep leaning back, eventually you'll tip. And no amount of trying to push yourself back up will bring that chair upright. The Earth system's very similar. If you apply a forcing, it can keep changing and return when you stop that forcing. But after a while, if you keep pushing it, it will shift into another climate state or environmental state. And no amount of reducing the carbon dioxide levels or anything else will return it back to what it is. And there's an awful lot of work in this, and I'm sure you've seen elements of this before. This idea of tipping elements or tipping points in the Earth system. You might have heard of things like the North Atlantic Ocean Circulation System shutting down, the Gulf Stream, it's popularly known as. The collapse of the Amazon rainforest, it dries out and eventually it can't be maintained, and eventually the rainforest all dies out and all the carbon goes back. But the one I'd like to focus in on the bottom, in particular on the left-hand side, the instability of a West Antarctic ice sheet. This is what John Mercer was talking about back in '78. If you melt the ice enough, because it's on the seabed, it can't grow back again, no matter how much you change carbon dioxide levels. The frightening thing as well, though, is that these are not all in isolation. You often hear, or people are working on this idea of the domino effect. When you do one thing, another thing happens. The Arctic sea ice is something you may have heard about. It's basically the planet's air conditioner. Sea ice forms on the surface. For those of you familiar with the Franklin expedition, he was trying to find the Northwest Passage. He got trapped in the ice. Effectively, they all died over 18 months. Now you can sail around in the summertime, go all the way around the pole. It's a route that's actually you can punch through from the Atlantic into the Pacific. When you remove that sea ice, you're removing that reflectance of the sun's rays, and the planet's getting warmer. As it gets warmer, it amplifies and gets hotter and hotter, with a knock-on effect for many of these other ones. So these things are actually interconnected, staggeringly difficult to work on. As scientists, when you start looking at actually where these tipping points and where they might tip, if you look on the far left, the column which is 2001, the orange and the red signifies where we thought those tipping points were. So that's the amount of heating the planet has to have on average before some of these tipping points kick in. So 2001, gosh, that was a long time ago. Well, not really, but it was around 3.5, 4 degrees warming. That's a lot. That's a lot of heating. Come through to 2018, we're now talking about 1.5 degrees of heating since the end of the late 19th century. We're at 1.5. Well, not 1.5 long term, but we've hit 1.5 as an annual record. Overall, we're about 1.3, 1.4, but the details are neither here nor there. The key thing is we're now in that danger zone where many of these elements could start tipping, and the West Antarctic is particularly important. So unlike Shackleton and Mawson, you can monitor from above. You can look at gravity, you can monitor at flow of the Antarctic, and you can see where the greatest amount of loss of ice is happening from the Antarctic. Now, this is an IMBY team, goes through to 2017. They recently just completed it to 2020. The same trend is there. You see the red areas off the West Antarctic. Interestingly, that's where the ocean waters are actually warming up the most. Has anyone heard of something called the Doomsday Glacier phrase? Yeah, a few of you have heard about it. That's basically where that is. Thwaites Glacier has got around 0.65 meters of global sea level rise in a single glacier. And effectively, work by NASA has shown that seabed warming, there's nothing to stop it. It's not locked in anymore to the land. It's going to fall into the ocean. The question is, how long is it going to take? And they call it the Doomsday Glacier because it's such a dramatic change. And of course, once you've done that, the rest of the ice sheet starts responding. And that is primarily driven not by warmer air, but warmer oceans. The ocean currents, because the winds are getting stronger, the oceans are coming up below and heating and melting out ice. Imagine putting an ice cube in a glass of water. Eventually, it's starting to melt. The foot is in there. In contrast, if you look at the peninsula, the point going up towards the South America, what used to be known as the Antarctic Andes, that's got some of the highest atmospheric temperature increases on record, about 3 degrees of warming. So you can talk about a global average of 1.5 degrees, but in some regions it's a lot more. And in Antarctica and the peninsula, you're looking at about 3 degrees centigrade. Now, many of you will be familiar with this as the international agreement, one of the Intergovernmental Paleoclimate Change meetings in Paris agreed that we would limit global warming or global heating to 2 degrees, no more on global average. And we'll ideally keep it below 1.5. At 1.5 is virtually gone. There's very little chance that we're going to stop that happening now. Virtually nothing. So the important thing is keeping it below 2 degrees. And now remember, with the tipping points, we're starting to get in that zone. We're actually in an area of danger. Sea level rise, though, is one of these things that's actually, it's rising. It's about 3.5 millimeters a year, give or take. Some parts are even higher. Off Sydney is actually one of the larger areas where it's warming and sea levels rising even higher. But the projections are typically in that sort of 0.5 meter or so, depending on how we keep polluting the atmosphere with carbon. But one of the big unknowns is the fact of just how quickly some of these ice sheets might go. So John Mercer talked about this idea of a marine ice sheet instability, because it's sitting on the seabed, and if the warm water can get underneath it, it falls into the ocean, effectively. But we don't know how quickly that works. And so these models and these projections don't include that, what they call low likelihood, high impact events. You talk to a lot of colleagues and friends who are working in this space, they'll typically say 1 to 2 meters of global sea level rise by the end of this century, far above what the projections are. I promise you there's hope, so we'll come to that. But you can't do everything remotely. You can't just monitor from afar. You still have to go south. You still have to go in boats or fly down. This is an amazing amount of work. There are many teams around the world trying to drill 1 million-year-old ice. Remember, it's really slow precipitation, but very thick ice. And the implication of that is it's very old. And the Europeans just announced, or just recently, they've drilled nearly a 3-kilometer long ice core all the way down, and they've almost certainly got 1 million-year-old ice. And the importance of 1 million years is that actually that's when the climate system looked like it changed. The ice age cycles were changing. You can extract the ice, and you can hopefully see those bubbles. You can extract the different greenhouse gases, and you can see the change in temperature and greenhouse gases, and they basically map onto each other beautifully. There's a slight lag as you warm things up, more greenhouse gases given off, which amplifies the warming even further. About 800,000 years or so ago, that looked like it had changed, and this ice core will allow us to actually investigate what the climate system was doing. The Australians are doing a great job as well at the moment, and they're finishing off their 1 million-year-old core. And there's a lot of other work going in this space, but there's going to be a lot of focus in the next few years about actually trying to understand what the climate system is doing in this part of the world and globally. You can't do it in Greenland because Greenland has got such large accumulation, such heavy snowfall, that actually you can't get back far enough. They don't go nearly as far back, maybe 120, 130,000 years. Antarctica is the only place you can go back to get these long-term records of this incredible, beautiful detail. So, sea level is another one that we should be looking at, because sea level affects us all. We're all seeing the impact of storms. We all know that actually it's not just a few millimeters a year, it's a few millimeters a year over time with storms on top of that. It's not just a gentle sea level rise. Now on the left-hand side, you can see where we are at the moment. We're rising in sea level. We're rising in carbon dioxide levels. But we can use parallels in the past. There's a period about 125, 130,000 years ago where the planet was 1 to 2 degrees warmer than today from natural processes, changes in the Earth's orbit, climate, carbon feedbacks. You've got slightly warmer temperatures, the ocean's warmed up. And sea levels, well, it depends on the data, but it looks somewhere between 6 to 9 meters. Some people suggest even higher, some people suggest a little bit lower. But the implication is that if you keep the planet at 1 to 2 degrees, somewhere in that order, which is basically where we are, sea levels should be 6 to 9 meters higher than they are today. The question is, how long does that take? That's the elephant in the room with this. And so this period, the last interglacial, is one of those periods where we can investigate that. So I wanted to show you some images of what we're doing down in Antarctica, just to give you a sense of how you might do this. Because as you could imagine, drilling a 3-kilometer ice core is terrifically expensive. Terrifically expensive. Tens, hundreds of millions of dollars. We've tried a different way. So we're going to show you what we're doing. And we're doing it with this amazing company called Antarctic Logistics and Expeditions, who operate out of the US. Some of the directors, managers are Australian as well. They operate out of South America. And you can fly, so you don't have to do the terrible trip on the boat if you don't want to do that. This is a 4.5 hour flight. Some of the times we were going down, this is an Aleutian, which carries all the gear. Nowadays you can fly down in a 757 and land on these amazing runways of ice. It's an extraordinary journey. It's about 4.5 hours. They even have in-flight TV in the seats if you want to now. Lap of luxury. But these companies, ALE operates, but actually it supports science, it supports expeditioners. If you just want to go down and see Antarctica, you can fly down with them, stay in these very nice tents, and then leave again. So, but they're incredibly supportive of our research. And so we've come to the other side of the West Antarctic ice sheet, the Weddell Sea. This is myself, just a couple of 100 meters above in a place called Patriot Hills. A couple of things to bear in mind here. Somewhere over the horizon, out at sea, is where Shackleton got trapped. But the other thing, and hopefully you can see this, is this amazing blue expanse. And these are what we call blue ice areas. These are blue ice areas. And I'll show you why that's important at the moment. The expeditionary work hasn't really changed much since the time of Scott and Shackleton. We sometimes use different tents, but these are pretty much the same design that Scott and Mawson and Shackleton were down in as well. This is the highest mountain in Antarctica, Vincent. You often find expeditioners going down there. You might have heard of the 7 Summits. It's quite a popular thing for people to do, climb the highest summit in every continent. So Mount Vincent is the highest one in Antarctica. So you meet a lot of expeditioners. I've never met so many people who've climbed Everest down there. But the light is extraordinary. Of course, during summertime, it's 24-hour daylight. It dips a wee bit during the daylight, but you get these incredible glows and red. There's no filter attached to that. That's what you see. In fact, it probably isn't really capturing it as much as possible. Almost pyramid. It's quite otherworldly, and it's extraordinary because you could be there, and one moment it's blowing an absolute gale, and the next you've climbed a peak that no one has ever climbed before. No one has ever climbed it, and you see a view that no other human being has seen, and it's completely still. And you and your friend are probably 100 kilometers from the next living soul, and you kick over a rock, and it just reverberates the sound. It's so still. It's almost deafening. You hear that expression a lot from people. And it's 24 hours darkness. So when you go down, light. So when you're down there, it's often hard to get your body clock to actually force yourself to sleep because you just keep going. Oh, it's just fantastic. It's daylight. It's daylight. So about day 2 or 3, you're just, I have to sleep. I have to pass out. But why are blue ice areas so important? This is just a schematic which Chris's team put together. And there's the Patriot Hills on the top left-hand side. These katabatic winds are these incredibly cold, dense winds that flow down from the plateau. So the plateau is about 2,800 meters. And occasionally what will happen is they're cold, they're dense, and they spill off a plateau and accelerate down to the coast. So when Scott of the Antarctic died in 1912, his team was trapped in a katabatic windstorm that went for, I think, 11 days. They think he got stuck for 11 days. It's incredibly powerful, but they're dry. It's dry wind. And so the practical upshot of which is that when these dry winds flow over the surface, first of all, it scours the snow away, but the surface of the ice, it doesn't melt, it ablates. It just disappears straight into the gas phase. And the practical upshot of which is that if you keep blowing the wind over and you keep ablating it, the gravity flows. And so although the ice is moving down the valley, which we call Horseshoe Valley, flowing towards the coast, there's this secondary flow at right angles. It's just gravity flowing up to replace the ice that's being ablated. Now that has amazing implications, because instead of actually drilling ice cores, you can effectively go along, here's Chris, with equipment you bought in Bunnings, and you can take as much ice as you want, which is fantastic. And it can go back tens or hundreds of thousands of years. And so here we've been working on the Patriot Hills. If you remember Michael Palin's Pole to Pole, I don't know if anyone saw that BBC series, it was a long time ago, but I saw it as a teenager and loved it. The company that flew him to the pole as Antarctic Logistics Expeditions, and this used to be their old base. So if we go back and watch the show again, this is Patriot Hills. This is where they used to fly. They don't fly there now. They fly around the corner at Union Glacier. But this is Patriot Hill. So this is this beautiful blue ice area, and you can see this lovely dimpling on the surface. And what you can do is you can go along with your drills, your electric chainsaws, your generators, and you can go back and you can find layers of volcanic ash, which are precisely dated. You can look at the greenhouse gases preserved in the ice, which actually makes a very nice gin and tonic, if you ever want to do that. You hear a lovely pop of the gases, bubbles. It's got amazing records of what's been brought on from the Southern Ocean, all the organic material that's come on there as well. And it's also got indicators of what the climate was like. So in one beautiful record, you've got climate, you've got greenhouse gases, and you've got age control for the volcanic ash and the dating. And effectively, you can go back through time. And what you see here, hopefully, is, or you get the impression, is that as you go closer to the mountain, the timescale becomes tighter and tighter because it's slower and slower as the gravity is coming up, it's steeper. And so we work across this surface. So it's steeper towards the Patriot Hills is around where we are now. And we go along, and instead of taking very small samples, we can drill and collect large amounts of material going up through the surface. And it's effectively a time machine. And we've had a number of papers on here looking at climate carbon feedbacks and Southern Ocean productivity. I'll talk a little bit more about this last interglacial when it was 1 to 2 degrees warmer. But it's a way of doing Antarctic research at a lot cheaper than the traditional way. And when we need climate data, this is super important because you know what it's like trying to get research funding. It's always a challenge. It's not always successful. Before you know it, you've lost 3 or 4 years just to get the funding, and then you still need to go down, and then you still need to get the analysis done. You can move very quickly with this approach. And ALE have got the logistics and provide it for a lot of the actual government agencies. I won't lie to you, it's not easy work. This is probably me on a better day, having a coffee. This is Zoe Thomas, who's a good friend and colleague, where we have these dome tents and where we'll actually end up, sometimes we'll sleep in there, but during the big storms, you can't be sure that that's going to survive a katabatic windstorm. And so often we'll hunker down elsewhere, and we're not sure if everything's just going to disappear. So far, touch wood, we've been lucky. But this is a sort of living space. But we're typically small teams, 4 or 5 people tops. It's very small. We can do a lot in that time. But normally I'm just, you're exhausted after a while, and you just, even that's the most uncomfortable surface in the world, you fall asleep very easily on this sort of material. It's very uncomfortable, but you can see how the level of detail that you can get on these amazing blue ice areas. And so just to give an indication of the sort of material that we're getting, this was published in Proceedings of the National Academy of Sciences. We were very lucky because this site in Patriot Hills is picking up volcanic ash from well-dated volcanoes. And so we've got the age control. And we can also then analyze for gases and also the climate. And what we find in between those 2 red arrows is basically a massive jump. The ice is 130,000 years old and older towards the hills. And then away, it's 90,000 years. There's a massive gap. And we think this is one of the first proof that actually when the world was 1 to 2 degrees warmer, a large part of the West Antarctic ice sheet did indeed melt. And this is some of the first physical evidence we've got. It's only possible because of this unusual blue ice area. So pulling back from Antarctica, what can we do? Because the implications of this are that the system is very sensitive. 130,000 years ago is not 2 degrees warming, it's actually a lot lower. It's super quick. The implication is Antarctica responds super quick. So what can we do? We do have some amazing solutions. If there's one single thing we can do, it's probably diet, actually. Reducing our meat intake is a phenomenally effective way of actually reducing your carbon pollution. Even a light meat diet is about half the footprint of a heavy meat diet. all sorts of amazing technologies about growing food close to source, even in urban areas. Building resilience, you might recognize this beautiful building. It's opposite UTS, absolutely stunning. Greening the planet, greening the cities. How do you take the heat out of multiple degrees centigrade? You certainly don't cover it all in concrete. You want to green it, you want to take the heat out of the system. That's a beautiful building. That's opposite the UTS tower, I think. So you've got this amazing contrast between different types of architecture, but that's probably going to be the future as we try to take the heat out of the planet and reduce the temperature extremes. Working together as a community, a lot of the time when we're working and dealing with these issues, people try to do it in isolation. It only works at scale. And actually, mental health-wise as well, it's really important to actually work with other people. So actually working as a community is a super important part of actually making a difference. And that can mean all sorts of positive things. You know, when we talk about tipping points, we often think of them in quite negative ways, particularly in climate and environmental science. Actually, it's a bad thing. Tipping points typically, well, it can work either way. And that's the important thing. And we see a lot of positive tipping points in the way societies works and the deployment of technology. We've all seen things where a particular technology suddenly becomes super popular and suddenly everyone's got smartphones and all sorts of different things. I'm going to take you back to the lovely 1980s. You might recognize some of these amazing people. The band of Aha. I'm the only one showing my age here. I remember Aha. Loved Aha. This was back in 1989. Norwegian team, a Norwegian band. Actually bought the first electric, well, arguably the first very high profile electric Fiat Panda into Norway. They refused to pay tolls. It took 48 hours to charge a battery and they drove it from, I think, Germany all the way up into Norway. Very high profile. And showing that actually that sort of technology can be applied. This is rather wonderful. We did a BBC documentary not that long ago, and this is the same wonderful people today. All got a bit older. But the technology's moved on tremendously. And that high profile is just one lovely example of what actually happened then in Norway. And for those of you not familiar, Norway, in large part thanks to the publicity of Aha, instigated a series of more and more positive measures to incentivize people to get electric cars. And you can see this lovely picture here. The oranges and the reds are diesel petrol cars back to 1990. And you see this takeoff from about 2010 as electric vehicles, plug-in hybrids take over. Now it's more than 90%, 95% of all sales in Norway are electric vehicles. Electrification, and of course assuming it's green sources in particular, is a big part of that drive to how we can get down. And that's a lovely example of a positive tipping point, and listening to Aha as well. I just want to finish up with just one example of some amazing work that's happening now at UTS. And it's a spin-out company called Algene. And the amazing things, algae. And algae is 40 times more effective at trapping carbon dioxide than trees and fixing carbon. And the beautiful thing about algae is there's so many different varieties and there's so many different applications. You can create feedstock for cattle, you can create organic material for building blocks, and you can make fuels as well. And Algene is being set up to change the approach. And instead of big algal ponds, you might have seen them like the sewage parks that you see around, the Algene helix system is one where actually the water is fed through this amazing helix, and you can then very effectively capture a lot of carbon through that algae and harvest it in a very small space. And the important thing with a lot of these technologies, and this is just one beautiful example, but there's so much amazing work happening in other universities, startups, is the idea that you can actually deploy these at scale and at cost that's cost competitive. That's the important thing. If this is going to make a difference, it's got to be as cheap or cheaper, it's got to be a better product, and it's got to be quick. Algene is one example at UTS where actually we think we've got a technology here that's actually going to make a big difference, and you can deploy it at scale around the world. I don't need to say this to you as an amazing audience, but you know how much research can make a difference in the world. And we're not shouting enough about how much research could make a real positive difference. The important thing is getting it deployed at speed and scale. And that's something that we take super seriously at UTS. As Christine said, I think the other thing is communicating the importance of research and science and what we can actually do about it. This was one attempt I had. This was with Uneffing the Future. This was with Imagine Entertainment. So this is with Ron Howard, the director Ron Howard. I had a chance to work with Hollywood for a podcast series. My darling wife, Annette, has been telling me for a long time I should try. I've written books. I suspect many of you have written books. Oh, it's hard work to make actually a reach with books. And most of the time people who buy a book, they already agree with you anyway. So you're just talking to your friends and colleagues, really. The idea for this was to try to reach out and actually engage a different community. And Annette had told me to do this for years and years, and suddenly it came an opportunity to do so. And so there's amazing people like the director Adam McKay, who I spoke to, who the Don't Look Up, a great movie on Netflix. There's a number of different people there who are doing all sorts of things where they're looking at different approaches that people can share and emulate. Not suggesting that you create a Hollywood movie, far from it. But Adam McKay's key point is actually we don't talk about it enough. We don't support each other enough. We sort of talk quietly to one another and then move on hurriedly. So this was my example. There are a few expletives in there, just to try to reach out, and it's got a terrible earworm jingle which gets stuck in your head. So apologies in advance if you listen to that. But you can have a look on the QR code if you're interested. But I just thought I'd finish off, and then I know we've got the point for discussion, but I just thought this is a lovely quote because this is such an important part. The research is not done, and the applications that are not done. And the great man wrote this lovely thing. He said, there seems to be a widespread idea that the work of exploration is virtually finished. The race is over. Ergo, the work of exploration is done. No more foolish mistake could be made, and none more disastrous in its consequences. There's a tremendous amount still to do in Antarctica, and there's an awful lot we can still learn. Thank you very much.